Okay, so let's go back. I want not to do the escape from an attractor. Right, this is where we were, I think. So exit the exit problem. So this is what we started last week. So again, we have a domain omega. I suppose that we have a dynamical system where all trajectories are flowing here toward the attractor. Right? This is what we have. So let's suppose we have a dynamical system x dot equals b of x. Point p0 or whatever p0, b of p0 equals 0. I assume that we have only one attractor. So, which means that, for example, if we look at the expansion, the Taylor expansion of the dynamical system around P0, what we get is, so B of P can be written, so the first part is 0, it's a linear part. It's going to be a matrix B multiplied by X plus O of X. And what does that mean? So this is for a point P, which is, let's say, this is point P, right? Where the point P has coordinate X, X1, Xn. So that means that locally, the linearized dynamical system, which I will write y dot equals b of y, this is the linearized system. The eigenvalues of the matrix B have their real part, which is negative. Right? If it's symmetric, they're all positive, and then they're all negatives. It is a symmetric matrix. Otherwise, the real part is negative for I going from 1 to n. Which means that basically all trajectories, if you start here for the no noise, all the trajectories are coming here, they are attracted. All right, so the domain omega, I assume that on the boundary, B dot n, that is the field is going inside. So when you have the field here, and you look at the normal of the domain here, so this is a normal to the domain, this is the vector field. This is, the angle is more than pi over 2, so that this scalar product is negative. So this is for, see, I call this B at point P. So for all P in the domain, in the boundary of the domain, I have this condition. This is the condition that the field, enter the domain. All right. And so what we said last time, we were interested in the stochastic equation. Which was x dot equals b of x plus square root of 2 epsilon w dot. So this is the deterministic part here. And then we have added the noise part with the epsilon, which is the amplitude of the noise, normalized here. I assume this is epsilon, which is small. This is small noise. Okay, and so what we were interested in last week is to look at the mean first passage time. So what we said is the mean first passage time is the solution u epsilon of escape, conditioned that the particle started at position x. And a couple of weeks ago, we proved that the mean first passage time, u epsilon, satisfy the mean first passage time equation, which is epsilon Laplacian u epsilon plus b gradient u epsilon equals -1. And since we're interested in the time it takes to escape at the boundary, so this is inside omega, we say that at the boundary, u epsilon has to be equal to 0. This is for all p on the boundary. And last time I gave you the example where we can find this structure. This can be found, for example, this is the potential when we do chemical reactions, the time it takes for a particle to escape from a well. So we say that if this is the distance, the potential well can look like this. And so what we'll be interested in is this region here. So this is V, this is the distance R. And so the escape of the well, which will be this region here. How long it takes to escape from here. This is the maximum. Well, this will be a bit different because then at the maximum, the field here will be 0. So it's not exactly this case, but never mind. It is enough. Okay, so we're in this situation, B dot normal, so here it pushes inside. This would be the case of discontinuity, for example. You arrive here with not with a tangent which is horizontal, but with a slope. But it makes some differences, but I'm not going to look at this right now. All right, so this will be our domain omega, and this will be the potential. And last week we said we take B, for example, equal minus the gradient of phi of V, where V is the potential here. And so to look at this question, we said last time, so let me summarize. We said that u epsilon, the property is that u epsilon, as epsilon goes to 0, it's harder and harder to escape. So basically, when you have particles here, if we start with a single particle, so it has some noise, it drifts towards the origin, moves sometimes here, and then it can escape. So we are interested in the time it takes, in average, to leave the boundary. So most of the time, of course, the particles, if you do simulations, or if you look at any problems related to this question, it spends most of its time at this critical point. So we said as epsilon goes to 0, u of x here should go to infinity. And so what we said even more specifically, it should be equal to a constant for any point x inside the domain minus the boundary layer. And in the boundary layer, there is a phi of x, which is called the boundary layer. So this is for x inside the boundary layer. I call B a boundary layer. All right, and so we said that this converges to infinity when epsilon goes to 0. And the question we are interested in is how to compute C epsilon and phi epsilon of x, which is called the boundary layer solution. This is called boundary layer solution, and this is called the outer layer. This is called the outer solution. So again, there is my class, which gives you the ideas, and then if you want to look at specifically, you should read, you know, the book of Schultz, the first one at least, the 2009 about theory and application of stochastic processes. And for all the theory about outer solution, inner solution, boundary layer solution, you can look at the books of Bender and Orzai. I think it's called something like asymptotics analysis. This is asymptotic analysis. This is a classical book about how you study ODE and PDE and the asymptotics. and to have more than just what I'm saying. But basically, this is a spirit. If you understand this, this is what we can find in any example of escape time, to have this structure of outer solution and inner solution.
So right here, but epsilon go to infinity.
Epsilon goes to 0. Yeah.
And then the first time will go to.
That's right, because if epsilon goes to 0, basically the time it takes to escape from the well, you see the noise. What drives you outside? This is the noise. So if the amplitude of the noise, if you are at the limit, you have no noise. The time is infinite. You're not escaping.
Yeah.
But the question is, of course, this is not enough. You want to know how it escaped to infinity. Is it log of epsilon? Is it 1 over epsilon? Is it exponential of function of 1 over epsilon? I mean, it's not clear. This has to be calculated. And so we said last time that the boundary layer, why there is a boundary layer? Because there are all the points that lies in here. So if you start in this region, then of course you can escape immediately without falling into here. That's why in this region, where we have to match in here u equals 0, this is where we have the constant, this is where c epsilon, and here we'll have phi epsilon of x. Just in this little band. That's why this is called the boundary layer for x in BL, means we're in this region. This is BL. Right, this is called the boundary layer, this red region. Okay, and so last time we started the analysis, we said that so I will use, sometimes for the potential I use either phi or v. It should be v all the time, but so if I do change notation, let me know. I'll go back to the normal one. Okay, so when b equals minus gradient v, we said that the equation, the mean first passage time equation, can be written of the form epsilon, can be written of the form divergence of exponential minus v divided by epsilon, gradient u epsilon, equals exponential minus v divided by epsilon. This is, we have shown that last week, right, in your notes. This is where we were. And so we said now, this is an identity, true for all points in omega. So I'm going to integrate right and left. Right, I can integrate this, dx, and this is dx. And the only thing I have also said is that let's divide everything, since everything is, I can always divide because everything is linear, divide by a maximum of u. So I'll divide here by u epsilon, 1 over u epsilon, where by definition u with the bar epsilon is maximum of omega of u epsilon, and this is actually the constant c epsilon we are looking. Let me remind you the picture. The picture is that this is a domain omega, that c epsilon, the function is constant inside the domain. It has to be equal to 0 at the boundary. Those are the two boundary points. And so we have not to glue like this. All right, so we have to look at this function here, and this is the function phi epsilon. We have to find c epsilon and phi epsilon, right? This is the goal. Okay, so now let's use the theorem of Gauss to change this into an integral over the omega. This is exponential minus v divided by epsilon. This is du epsilon. So this is the gradient at the boundary. So this is du dn. ds. And this is du dx. 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 And this is again divided 1 over the maximum u epsilon equals 1 over u epsilon exponential minus v divided by epsilon. Now I want to make one remark, is that the function, let's call v epsilon equals u epsilon divided by the maximum of epsilon. This, because the maximum is u epsilon, the maximum, what is the maximum of v epsilon? It is 1. This is 1, because it's normal, because this is a maximum. And it satisfies, we'll need this equation in a few minutes, epsilon, Laplacian v epsilon, plus v gradient v epsilon equals minus 1 divided by u epsilon. I just divided everything by u epsilon in there. Okay. So now let's start to understand what we are looking at. So u epsilon divided by this, by the maximum, I replace it by v epsilon, right? So I replace this by v epsilon. Okay, so now what does this say? This says that basically we are stuck. We have one equation and two unknowns. One over the maximum, which is the speed at which it goes to infinity, this is unknown. And the derivative of this, which is the derivative of this at this point, which is the high slope here, very high, that we have to calculate. So we need to find some more information somewhere else. You understand? Two unknown, 1, 2, and one equation. Usually to solve a problem, we need the same unknown and same number of equations. If the equations are independent, you can solve it. All right, nevertheless, we are going to start analyzing this equation. When epsilon is small, have you ever heard about the possibility to calculate this integral? So how do we calculate this integral of exponential minus v divided by epsilon dx of, do you know how you calculate this?
Expanding at infinity.
This has a name. This has been looked at 200 years ago, or even more. Never heard? This is in quantum mechanics. People are using it a lot. No? This is called the Laplace methods. You know, never heard of this? So what is this equal to when epsilon is small? What is the asymptotics? So you are going to use the Laplace expansion, Laplace method. The Laplace method says, what does it say? Suppose, for example, suppose we have a potential V. Here we can actually have, instead of one, we can actually have several minimums. Suppose you have minimum here of a potential. What is this equal to?
Feels like the largest contribution.
Yeah, and the largest contribution comes from the well of the deepest well, not from the one here, the deepest one, because it has most of the energy. Or what happens is that also what can happen in this, when we have what is called situation with double wells, is that they can have several wells. It's a very degenerated case. Usually that never happens. But it can happen when you have some little fluctuations here, so it's not that sometimes it happens in real life. You can have many wells with the same energy, so that the difference of energy is the same. So you've seen this before, how you calculate all of this, so I don't have to redo it. So you do, this is exponential v minus, you take the minimum of v, that is, this is the minimum here of v. This is this line. V minus minimum of v divided by epsilon dx. And I multiply everything by minimum v here divided by epsilon. So I have added, because it's exponential, I have added and subtract minimum, right? So it's exponential, I put it out because it's multiplication. And this v minus minimum of v, how you calculate this integral, you just take bolts around this minimum, where you can do a Taylor expansion, and outside it's going to be negligible. I did that on the internet. There's an internet class. I spent half an hour explaining this slowly. So you should look in YouTube. My YouTube class about the Laplace method. But basically, we use v minus minimum of v. So what is it equal to? Yeah, the first, so this is now we do a Taylor expansion. So Taylor expansion says that we have to look for the first term. The first term, if you add the minimum, this is 0. And then so because it's a minimum, we have a quadratic positive matrix in n dimension. So which is the sum. Let's write it this way. This is the second derivative dxi dxj at point. So if we are, let's call this the family of point p1, p whatever pk. Yeah, pk. So this is, let's say, at point p or any of these p's. P. Let's do it at the first one, p1. So we sum from 1 to n for an n dimension, and this is xi, xj, plus something which is of order O of x squared. And there is 1/2. Right? So this is the Taylor expansion. Now you can always change coordinates because this is by definition a symmetric matrix. V is sufficiently regular, so it's symmetric matrix. And it has to be positive because this is the minimum, right? Imagine a parabola. So we can always find a coordinate system such that we can diagonalize this. I mean, we can always do that here. So this is 1/2 of the sum of lambda j y j squared plus y squared. And all of the lambda j's, I will call lambda j's at T1 here because this is the first point. They are all positive, strictly positive. Right? So this integral is going to be calculated. Again, you look at either any good books on the Laplace methods, or you can look at the presentation I did on YouTube. V of x minus v minimum. So, okay, we have this now. Let me replace everything in here in this integral. The integral of exponential minus v divided by epsilon dx can be written really as the sum of the contribution around the ball of radius delta at point pk. You have to solve for k equals 1 to, I don't know how many points we have, let's call it m. Now m minimums here, so where the point pk are the v is minimum at the point p1, pn. So this is the sum of exponential of v minus, so v minus v min this way. So I put out the V min divided by epsilon, right? And then in this neighborhood, I'll use this Taylor expansion through this away. And this is one exponential of lambda j of pk. So it's not necessarily the same frame that I'm using, but I will still write for all of them yk. So this is yk. So this is the sum for j, so this is yj squared. And then we have the product dy1, dyn, plus something that is negligible with respect to this exponential. So this exponential minus v min epsilon, and actually this is of the order of exponential delta. We can show that outside this, because you have a gap, v minus v min is bigger than delta. Here you can even write this is minus delta divided by epsilon, right? Because outside the minimum, if you have a minimum, if you have a parabola, if you are at a distance delta here of this, that's for sure that your function v minus v min is above a certain something. It's not exactly delta actually. It's maybe square root of delta. So let's call it delta tilde. But delta tilde is strictly positive. Right? So we know that this is going to be very small, exponentially small compared to this. Now, what is this equal to? So, wait, I have forgotten something here. We have to divide everything by epsilon. So how do you calculate this?
Not a Gaussian integral because
Yeah, almost.
almost we have to go from minus infinity to
Yeah, instead of being a ball of radius delta, now we have to change variables so that it becomes, we write it u I equals y I divided by square root epsilon, so that this is going to be the integral. So this is, I will rewrite everything. So equals here is the equal that is here. This is the equal. And so we'll have the sum of exponential minus v minimum divided by epsilon. Integral from b of pk divided by, so when y equals delta, so this is going to be, so for y equals delta, u is equals delta divided by square root epsilon. And then this is exponential of minus 1/2 of the sum of the lambda j of pk, sum for j from 1 to n, of uij squared divided by nothing. And this is dy du1 dun. And then how many square root epsilon we have? We have square root epsilon to the power n, because we have n term. All right, so now asymptotically, when n goes to infinity, since all the terms contribute similarly, this we can replace this by what? Since this is an integral that converges when epsilon goes to infinity, right? So now we can replace this by, yeah, which is the entire space. So this is equal to, so now this is we write approximation. So the sum of the point k exponential minus v minimum divided by epsilon. Now we have the Gaussian integral, 1/1/2. So right, so I will integral for Rn of this Gaussian integral, which is exponential of minus 1/2 the sum of lambda j pk uj squared, and then we have to divide everything here by epsilon to the power n divided by 2 du1 du n. Now what is this equal to? This is classical Gaussian integral, and
Pi to the n half over determinant of.
yeah, actually we can even split it, because this is not the integral of n times the
It's just
same
multiplication
of the same line, because they're all separated. You know, this is the sum. If you have integration of R2 exponential of x squared minus y squared, this is you know, the integration of exponential x to the power 2, because this is all right. So this is exactly what we're doing here, and so you all know that the exponential integral of exponential of minus lambda x squared dx, this is equal to r.
Square root of pi.
This is pi divided by lambda square root, right? So we'll apply that in here. Lambda equals to what? So this is finally equals to, so this is lambda is, so this is lambda j, so this is pi. Lambda is lambda j divided by 2, so there is 2 pi, divided by the product of the lambda 1 pk, lambda n pk, and there is a square root, so this is square root of this. So the leading order term is this. And this, the product of this matrix, is actually, we can always write this. This product, the product of lambda j pk, this is exactly the determinant of the SCN matrix of the matrix of the second derivative of dxi dxj at pk. This is product j equals 1 to n. By definition, this is exactly this. So this can be expressed in terms of the second this can be expressed in terms of the second derivative of the potential. All right? Summary. We did all of this to show that this term, when epsilon is small, which is the case, is this. Right? Okay. Now, we haven't moved much in terms of the rest. We need not to estimate. If we are interested in calculating the rate at which the function goes to infinity, now we know this. If we know this term here, we'll have it as a ratio of this divided by this. This will give us this ratio. Now, how are we going to study this term here? What is the difference between this and this? Okay, what is similar? The similarity is, suppose this was 1. Suppose this is 1. How do you estimate this?
Derivative with respect to the volume.
Look, if this is 1, what is the difference between this integral and that integral?
It's the volume.
This is the volume versus surface, so you would redo the same, except that we are on the boundary, and that's it. So we'll have to do a Laplace method on the boundary, period. So now the only difficulty is to understand, to calculate this. Once we have this, we'll have a function here, and we will do everything. And if we have a function here, now we understand that what is going to be selected is going to be the minimum of v on the boundary. So here we selected the minimum inside the domain, and now we are going to select the minimum of v on the boundary. So now we know that there is a minimum here, for example, if we have one attractor, And then we are going now to look at the minimum of V at the boundary, and to have, for this guy, what we are going to do, we are going to get the Taylor expansion of this at the minimum of this guy, so that we can continue. We will exactly do the same thing as we did here, which is calculate this, and that will be multiplied by this function. And when we will be ready to be around each of these balls, we'll use here the Taylor expansion of this at the point pk. All right, so now this is the mission. But before doing this, we need to calculate this. So where this function is calculated, this is exactly in this boundary layer. And we are exactly at which point? And this is this, what is this dvdn? If this is the domain, this is exactly the derivative of v at this point. So this is what needs to be calculated. All right. So this can go. Right, this is a very important proof, for example, because this is everywhere in chemistry, everywhere in statistical physics. You need to have been through these calculations. And you should redo it for yourself, because with this you can really look at all this problem of residence time of particles and how this is calculated. Okay, so now how are we going to calculate dvdn? So let's first prove that outside the boundary layer, V converges to a constant. I haven't proved it. I told you it is, but I mean, we found it because we said that if you start at a different point, because you're going to converge initially to the center, basically it doesn't matter where you start. How do you prove it? So for this, we are going to use this equation. So what is the limit of V epsilon? Okay, so V epsilon is the solution of this equation. So here we're going to use a little bit of mathematical technique. So which is epsilon Laplacian V epsilon plus B gradient V epsilon equals to -1 divided by this constant C epsilon, which goes to C epsilon goes to infinity. So this will converge to 0. Now, how do you study convergence of a function V epsilon? Well, in mathematical settings, this is an equation, so you can multiply by a function phi, and you integrate over the domain. So now I assume phi is a function with compact support. That is, it's 0 outside the ball of radius epsilon, or of radius, I'm sorry, whatever the radius. And I suppose that phi doesn't meet the boundary. It's really inside the domain. Right? It is, the support is not touching here the boundary. Now, what is the limit of this? We said that V, the mean first passage time, is positive because this is the time, and it is less than 1. Now, what is the limit of this term when epsilon goes to 0? If this is true for any function phi with compact supports, this is true for any function here, which is even regular inside the domain omega, Then if you integrate by parts twice, we get epsilon integration of phi Laplacian v epsilon equals v epsilon Laplacian phi, because the integrate term are 0. If you integrate this by parts, you obtain this, because phi has a compact support. This compact support. So this is this term. Now, if you multiply all of this by epsilon, and if you multiply all of this by epsilon, clearly, you know, the absolute value is going to be less. This is v epsilon, which is less than 1. This is integral of whatever the Laplacian phi is multiplied by epsilon, and when epsilon goes to 0, this goes to 0. So this converges to 0, this converges to 0, which means that this has to converge to 0. And this is true for any function phi. So v epsilon, we can prove that v epsilon converges to some topology, which I don't go into detail, to a function v, as epsilon goes to 0 inside the domain, which is solution of the equation b gradient v equals 0. How can we conclude from this? You know, this is b gradient phi, b gradient v. So this is true for all functions v. So this is the limit equation. Now let's conclude that v is constant. Why v is constant? How do you solve this first order equation? You've seen this in apply math? How you solve first order equation?
What's b here? Sorry.
I'm sorry?
What is b? Is it the same b as the one?
Yeah, b is here. This is the b, this is the vector field. B is the vector field. B was equal to, you know, minus the gradient of v. So how do you solve first order equation in mathematics when you are in a domain? This is known from since maybe 100 years now, maybe more, by the methods of characteristics. Yeah, so what is the characteristics? So let's use the methods of characteristics, which is very elementary here. Method of characteristics. That is, we'll take the solution of the equation x dot equal bx. Those are trajectories. We showed that at the beginning. You remember? This was the characteristic that all trajectories were converging. So those are the solution of this equation. Now if we take v along those characteristics, that is v of x of t, and if you differentiate this with respect to this time, what do you get? You get v, so this is gradient v, multiplied by x dot. By definition, x dot is b of x. So this is gradient v multiplied by b of x. But what is this equal to? 0, which means v has to be equal to constant along the characteristics. So v x of t equal constant. So if you start at position, any position x inside, remember we're inside the domain. If you're here, so this is constant, so you can go to t goes to what? If time is positive, which direction are you going? This way or that way? We said that the field is an attractor. So where are we going?
And go in the middle.
Yeah, so, and when do you arrive here? For time equals? Infinity. So you arrive here at infinite time. So which means that when we go to time goes to infinity, this is a constant that depends, if I start at position x0, it's a constant that depends on x0, but if I start at position x1, I have also a constant that depends on x1. But I want to show that it is independent of the position. So why is that? Because when t goes to infinity, they all meet at one point. And since v here, this is a continuous function, this is a continuous function. This means that when t goes to infinity, this converges to v at point p0. And so for any point, any other point x1, because this is constant in x0, x1. So we have shown here that it is a constant. So v inside is constant. Again, we cannot go to the boundary because it cannot be true that it is constant at the boundary, because at the boundary it has to go to 0. And what is actually this constant equal to? So we have just shown here that v is constant. So what was the maximum of v? We say v epsilon, maximum of v epsilon was equal to 1. So when this is over omega, so if it converges to a function v, maximum of v should be equal to, v is a constant. So if it is a constant, we have v equals to 1. So this is a constant 1 in here, inside. That's why this was the constant c epsilon. You with me? We said v epsilon here. We said that the maximum of v epsilon is 1.
Yeah, but then in that case, all the u epsilon is the maximum.
I'm sorry?
So in that case, then all the u epsilon should be the same. Right. So
This is the maximum. So for example, you have the maximum of the function, which is this point. So this point, and we said that when epsilon goes to 0, everything converges to something that is going to be flat. And since we know that at least one point it is exactly 1, it has to be 1 at infinity. This is all what we said. Okay, so this resolve, we haven't done much yet. We've just resolved here, inside. Now what we have to understand is how you glue something, a function that is equal to 1 in here, with something that has to be equal to 0 in here. It has to be glued such that it satisfies the equation. Right? So the final step is, now we have shown that v epsilon converges to 1 inside the domain. And now we have to glue it here to something that equals to 0 by definition, because we have this boundary condition. And this will tell us exactly what is the boundary layer. So how do you get information about this? And if we have this, in some sense, we are good, because this is exactly what we were looking at. Okay, so how do we, if we can calculate this function, we'll put that into here, redo Laplace, and get this. But we cannot use anymore this equation, because now we want to extract this maximum as a function of this. So how do you get this information about this? You have to go back to this equation. All right? So how do we do this? Let's consider the domain. All right, so the domain is whatever. We have the field that is converging to the point, to a critical point. And so let's take, at any point, we'll take a frame. So this is, so we take, at this point, we take the normal. And then, so this indicates one direction. And so if this is a space of dimension n, this perpendicular to this is a space of dimension n minus 1. So now we have a coordinate along n. So this is a normal that point this way. So this is x1, and so we'll have x2 and xn. So perpendicular we have the x2, x3, xn. So we have n minus 1 direction. And now we are going to look at this Laplace equation using this framework x1, xn. So what do we get? We get Laplacian v epsilon plus b gradient v epsilon equals minus 1 divided by c epsilon. Okay, so let's write it now in this coordinate system. So epsilon Laplacian, this is epsilon dd v epsilon dx1 plus dd v epsilon dxn plus b gradient, so the field, the vector field is, so this is a vector, so it has coordinate b1, bn. So this is b1 of coordinate x1, xn, dv epsilon dx1 plus bn x1, xn, dv multiplied by dv dxn, and everything has to be equal to minus 1 divided by c epsilon. All right. So let's now look at each term separately. As epsilon goes to 0, c epsilon goes to infinity, so 1 divided by c epsilon goes to 0. Okay. Now, let's start to think about what happened. What is dv epsilon dx1 doing at the boundary? What is the shape of the slope? That's right. It's going to be steeper and steeper and steeper, which means it goes to vertical, which means yeah, what is it is going to infinity. So which means that this may blow up to infinity. So something that can go to infinity, which is only dv derivative when you differentiate with respect to x1. Because when you are perpendicular to this, everything will be flat. So then if you differentiate something that is flat, this is 0, constant. That's right. So dv dxn, the rest term here, will be of order 1. B is known. B is, so now, which is the only term? So now we have to have something equal to 0. This is equal to the sum here, which is constant, doesn't go to infinity. This one can go to infinity. So if, what we have to make sure about this term, to make sure that we have something that remains infinite in this system, what do we have to make sure about this at the term, at the boundary?
It remains infinite.
Which remains not equal to, yeah, to have, if this goes to infinity, how to make sure that the products still go to infinity. What can happen is this can be equal to, if this is equal to 0, 0 multiplied by infinity, we don't know what that is. But if this is a constant like 1 or whatever, the 1 multiplied by something that goes to infinity goes to infinity. So what is b at, what is b1? What is b1 at the point here? It is, why is not 0? Yeah, we erase it. Okay, what is b? What is b1? What is b1 at the point 0 here? I call 0, I call it 0, 0. This is the center of our frame. What is this b1?
It's the derivative of the potential in that direction.
Yeah, so b1, it's exactly b projected on the vector n. And so what do we say at the beginning? B dot n was, this was the condition. It was strictly, we said that everything goes inside. So B, we said that B was going this way, while the normal was going this way. So this is, by definition, this is negative, and this is finite. It's not zero, because B is not perpendicular to n, right? So this is our B. You know, you remember, we said that everything is converging. So this is B, and this is a normal.
It must be parallel to n. Because we chose the border such that it's parallel to n.
Yeah, yeah. No, but I remind you now we choose it exactly like this. So B1 is exactly B dot n. It's exactly the component. But well, we can have a situation where this is B, you know, and the border, the domain is like this. It's not exactly that B is exactly the opposite of n, but it has a component in n which is exactly negative. This is what is important. Okay, so this term says that this is not zero, it is whatever, it's a finite number. So if this goes to infinity, this is going to be infinite, that's for sure. I'm not going to compensate something that is infinite, and this is zero. So now what can compensate in here? Something that will go to infinity. What is the only possibility is what? Okay, what is the derivative with dx2, dxn? This is the derivative which is perpendicular. This is x1 here. Now the derivative in x2, xn, this is a derivative in this direction. So this is again, as the function is getting flat, that should be of order 1. The only possibility to counterbalance this term is to use the second derivative with x1. Right? So we're going to look for a solution. We're going to look for a solution v of x1 xn, which is of the form, let's call it f of x1, and then g of x2 xn. Take this, plug this into this equation, and let's see what we'll get for f and g. Right? So if we have this, the only possibility, because they have separated variables, okay, let's do it. So you know how to plug this. This is when you separate variables. So you have f prime divided by f plus epsilon. So this is Laplacian. All this 2 to n variables g divided by g, and then there is plus b1 of f prime divided by f, plus then we have to sum. So this is ddj dxk, ddj dxk, bk, and the sum for k equals 2 to n, and this is equal to minus c epsilon f and g. And this, I'll put here 0, because as epsilon goes to infinity, I would say this is almost 0. Okay, so in order, so if you, or you can also multiply f and g by everything by f and g. So in order to compensate this term that goes to infinity, the leading order terms in the equation would be this plus this has to be equal to 0. This is the leading order term, because the rest, this term plus this term is going to be of order 1, and this has to be equal to 0. So if you have two terms that goes to infinity, this has to compensate this. So we end up here with the equation that epsilon f second plus b1. So this is b1, this is the coordinate, right? So this is b1, x1, x2, xn. F prime equals 0. This is the important equation for looking at how this term is going to compensate by that term. So what does this say about f? So f now is a function of only one variable, of x1. Where have we written the decomposition? Yeah, here. So f is now a function of one variable. So how do we solve this?
Perturbation expansion.
What?
Perturbation expansion.
Yeah, we can solve it now directly. So what is it? What is it? What is, so now we have to solve this for x1. So what is the general, so x1 here is going to vary in a little bit, a little. So I will freeze the coordinate x1 here to simplify. Let me freeze this at 0. So, because we're interested, right, in what happened inside and then, this is not the boundary layer. So x1 is going to vary in a little interval. Now b is a regular function, so b, when you move a little bit, is not going to change much. So let me freeze this and take x1 here equals 0. I freeze. We do a Taylor expansion at this, and I don't care about the rest. Now, this is a linear equation in terms of x1. It's even something that you can integrate now. What is it equal to? So how do you do this? First of all, you can integrate once. This is constant, this is second derivative, this is independent of x1, and this is the derivative, so integrate once. What do you get? You get epsilon f prime plus b1 of 0 x2 xn f equal a constant. I don't know what is this constant, it can depend on x2 xn minus xn, but not on x1, that's for sure. So that if you differentiate with respect to x1, this is 0. And now you can integrate once more. How you integrate a first order differential equation? You use the classics. This is you divide by f, right? So what is this? What is epsilon f prime plus a f equals 0? So this is divided by f. This is a divided by epsilon. We integrate 1. This is log of f plus a divided by epsilon x1 equals a constant. So the function f is equal to f of x1 xn is equal to a constant exponential. So if you do it this way and you put exponential everywhere, minus a, so a is what now? A is b1 of 0 of xn divided by epsilon plus another constant, right? The solution, you have a general solution of this equation, which is a constant. If f is a constant, this is 0 and constant, and so f has to be equal to this constant divided by this. So I'll write it in a general constant that depends on x2, xn. And this, again, this is not the same constant. This is constant 1, this is constant 2. Again, constant means in x1, so it's 2 xn. Okay, so now what is the general solution? So I know I multiply, to get v epsilon, I multiply by another function, which is the function g here, which is also of x2, xn. So finally, if I multiply everything here by g, I get v epsilon of x, which is g2 g of x2 xn multiplied by f of x1 xn. It's finally the same thing. I can call it constant 1. I rename it, but it's also constant. I don't know what it is yet. Plus a constant 2, constant in x2 xn, exponential minus b divided by b1 divided by epsilon of 0 x2 xn multiplied by, I forgot something here, multiplied by x1. Very important, right? Because we have the x1 here. All right. Now, next. We have moved quite a lot here. What is v at the boundary, by definition? At the boundary, v is equal to, what is the mean first passage time condition at the boundary? 0. All right, so for x1 equals 0, now we are at the boundary for x1 equals 0, this plus this has to be equal to, all right, which means this equal minus this. So I can just take it out and write this on the form of 1 minus this. All right. Now we need to understand one more thing. We need to find out this constant. How do we know this constant?
I mean, we know that v epsilon is bounded, right?
The epsilon is bounded, and what do we know about v inside the domain? 1. So how do you go inside the domain? What do you do? x1 has to go to, yeah, I mean, it has to go inside, it has to go in here. Now let's look what happened when int x1, so let's do the proper x1, it goes in here. So this, the normal here is here. The normal is in this direction, so this is, so in b1, this has, b1 has to be, b1, what is b1? It's b, no, wait, I made a mistake here. b1, it's the projection of b with respect to the vector I, and the vector I is minus n. Right, if you have a vector, coordinate vector, right, when you project, and if this is a normal here, this is you project on I and j. So this is positive, and this is negative with respect to the normal. So this is minus, yeah, so this is correct, but I is minus n, so this is minus bn. And we know that b dot n is negative, so b1 is positive. All right. Why are we saying this? Why are we saying this? Because now you exactly said it. If you want to get the information about the 1, we know that the function is 1 in here. So let's send x1 to infinity, which means, or x1 actually divided by epsilon, which is what I should have been doing from the beginning. But x1 divided by epsilon, when it goes to infinity, all of this converges to 0. So which means this constant has to be equal to, that's it. Because we work for it. It doesn't come from free. We work. We say that this constant has to be equal to this. So finally, we get in the boundary layer for x now inside the boundary layer, we have v prime v of x equal this. Now this is great. What do we need ultimately? I think I have erased the master equation. We saved half of it, and the other half is killed. Now what was left? We were trying to calculate the integral of the exponential of v divided by epsilon d v epsilon, you remember, dv dn, d surface along the omega. We're almost there. We don't have, so what we did here, we said we have this expression in a small band. So now how you go from v to its derivative? We have to differentiate. Differentiate with respect to what? With respect to the normal. What is the meaning of differentiating with respect to the normal? The normal, if it was this x1, it would mean differentiating with respect to x1. So these are almost the same, except there is a minus. So this v dv dn, this is the derivative of v, and this is really gradient v multiplied by normal. And since the normal is exactly equal to minus I, this is exactly minus dv dx1. And now what is dv dx1? We can have it in here. So this is trivial because this is the differentiating an exponential. Now this is what? 1, this goes to 0, and now we have to differentiate this. So this is v1 of 0 at position. So this is exactly now the derivative at position 0, which is here, this point, divided by epsilon. And now we have to take this point where? At the boundary. So this is exponential at this, at point 0. Because we have to take this exponential minus b divided by whatever, x1, and we have to take the expression of all of this for at 0, actually, exactly at 0. At 0, but so this is exactly 0 because this is 0, and so this is exactly 1. So we calculated exactly what we wanted. This is exactly b at the position where we took all of this, and now we could do that at all points along the boundary. So this is equal to what finally? This is equal to integral of d omega of exponential minus v divided by epsilon, and this is the let's call it so b1, it's exactly minus b dot normal. This is the vector, the component, the negative component of the vector. And now we can repeat this procedure along all the boundary, and yes, we have to divide by epsilon ds Now we have to do Laplace methods on this. You're with me? That's why it's not, if you are interested in this, it's not a good idea to miss this class. All right. We are almost done. I'll keep this because this was the right-hand side, you remember? This here. So now you are working, now I'm tired. What is the Laplace method of this term? This is equal to what? We have to take the, how do you do Laplace method on this function? We have to, when epsilon goes to 0, it's true that we are dividing here by epsilon, which tells us actually exactly how the slope here was going to infinity. It went like 1 over epsilon. This is what we see from here. So, where shall I take the, before I took the minimum of which function?
The potential.
Of potential. Now I take the minimum of the potential, except that I'm now on the boundary. So this is exactly exponential minus v, the minimum of v, but now I'm on the boundary, d omega, divided by epsilon. All right, so now this is a function. So I can use exactly all of what I have calculated here, except that in the sum here, I will get this function. Okay, let's do it slowly. So this is the sum of the integral of exponential minus v minimum divided by epsilon. And now I'll take this, so this is around the ball of point qk. So I'll sum over k from, let's say, 1 to whatever number, whatever I have. So let's call it capital N. B of qk of delta. This is a ball on the boundary, multiplied by minus b dot normal at a point P on the boundary. I mean at the point, ds P, and the rest I will neglect. Right? So now if we apply the Laplace methods on this.
Where's the epsilon going? Or why can we...
I forgot. Divided by epsilon. Okay, so now let's continue. So if you do Taylor expansion of this, you're going to get this. So this is the sum of d qk delta divided by the same thing I have to divide it by square root epsilon of exponential minus 1/2 of the sum of lambda j, except that now, if the space is of dimension n, the boundary is of dimension n minus 1. You know, if you are this is dimension 3, the boundary is dimension 2. So this is n minus 1, and now this is lambda j, p whatever, or q k, u j squared, du1, so no, I forgot this term, minus b dot normal at point P. So if I do a Taylor expansion divided by epsilon, dsp. So if I do now a Taylor expansion of this at this point, qk, I can pull out here, you know, I have integral of a function of x, exponential of x squared divided by epsilon. Why I do have, sorry. So if I do this, okay, there is one step here that is missing. If I have a function like this in dimension 1, I'll come back to this in a second. Now if I take u equals x divided by square root epsilon, I can write it this way. This is phi of u square root epsilon exponential minus u squared du. You agree? I just did. So now what I'm going to do is to replace this function, because when epsilon goes to 0, this goes to 0. So I can put that out and get the integral of this. Right? You agree with this? So this is what I'm going to do here. So this is point. This is b at point square root p dot normal. Now I'm going to replace this by b at 0, which means at point qk, where we are on the boundary. I'm going to erase this now. So just to explain. So this is equal to this, exponential minus minimum of v d omega divided by epsilon, and then the sum from 1 to n of all of this. And this is going to be equal to, I pull this out, this is exponential minus the minimum of v epsilon. So this is going to give us a sum from 1 to number of minimum point. So if I do this, it's exactly the same calculation. I'm not going to repeat it. So you get what? You get 2 pi to which power? Now we are at power. Yeah, here we forgot to write 2 pi to power n. Now here is 2 pi to power, if we are in dimension n minus 1, it's 2 pi to n minus 1 of the square root of the determinant of the same thing, which we wrote last time was the determinant of the SCN of the potential restricted to the boundary. So this is the SCN at the boundary. Multiply, so this is not a new term, minus b dot qk dot normal divided by epsilon. And then we have to sum over all the minimum points on the boundary. We are missing epsilon. Yeah. And also there is an epsilon to the power why this is divided? Because x, this is multiply, no? L to multiply, because when we had this dx1, so this dx1 dxn minus 1, and we said u equals square root u equals of x, right? U is square root epsilon x.
The other way around.
Or yeah, x equals square root epsilon u. Thanks. So dx1 dxn, yeah, so we have to multiply by epsilon. How many epsilon do we have? It's epsilon 1/2, and we have n minus 1 of this. While here it's not, why it's divided here by epsilon? It should be multiplied, no? Yeah, maybe because so what is the term here that we get? This was from the first, this should be this, so this should be equal to the sum of k of exponential minus the minimum of v over the domain divided by epsilon, multiply by 2 pi epsilon to the power n divided by 2, multiply by the determinant of the SCN. This is square root of the determinant of the SCN, and the second derivative of phi dxi dxj at the minimum point. And the minimum point, there was So as the point P1, P whatever, PM. Okay, so let's summarize everything. I don't have any more the formula on the board, but the formula was integral of d omega exponential minus v divided by epsilon multiplied by d v epsilon dn ds was equal to minus or plus or minus c epsilon integration of minus v divided by epsilon omega. This was our formula from the beginning. Now we did calculate this. This. And now we have calculated all of this, which is this. Now you are going to work, and you are going to tell me what is C epsilon, that should go to infinity. C epsilon equals this divided by this. So which means 1 exponential minus v divided by epsilon divided by integral of exponential v divided by epsilon dvn dn. So who is going to give me the expression? You have to work a little bit now. You work 5 minutes. Wash my hand, and then we'll finish with this.
Yeah, let's do it.
This is for people who like big formulas. Okay, this is what you got? Yeah? Now what is this formula? Do you recognize this formula? Have you seen some of this formula? So there is a minus and minus, so this should be plus. And why we have a minus here?
Which term? The
B dot n, B dot normal.
So we said it was B1 is in the opposite direction.
dvdn should be dvdn, v is positive function, so dvdn should be b dot normal. Why do we have a minus? Okay, we have to track, maybe there is a mistake of a sign here. I'm not sure about this minus here, because there was a minus before. Okay, we will resolve this later. So this is, now we can make, let's make some simplification. 2 pi n divided by 2, 2 pi epsilon n minus 1 divided by 2, we are left with what? We can, this is like n minus 1 plus 1, so this is exactly this. Agree? Now, there is an epsilon here. Are we good with the formula? I think this was the correct formula, right? So C epsilon was exponential b divided by this. Is it correct? This formula exists from the beginning. Looks okay, no?
I have an extra epsilon
What?
on the
All right. We have an extra epsilon somewhere.
on the right hand side.
Here, it's epsilon like this. Oh no,
Yeah, it'd be the same.
this is
So
correct.
we're dividing on the right hand side, so yeah, it's the same print.
This is correct like this. Okay. So then there is, we have to multiply by epsilon. We have to divide by epsilon here. Okay, great. So this epsilon goes out with this epsilon. Right? Okay? There was an epsilon here. So C epsilon, I divide everything now by epsilon. So we have this epsilon and we have this epsilon here. So epsilon goes out with this epsilon. Okay, and now this is the sum. So this is now exponential and this exponential, I can put them back together. So this is minus v, this is exponential minus minimum of v omega minus the minimum of v over the omega. This I can remove. Alright, so I can now write this equation of the form 2 pi epsilon 1/2 exponential, a constant here, divided by epsilon, and here there is a function, whatever, that is independent of epsilon. So I call this a constant k. And tau epsilon is exactly the mean first passage time. So have you seen that before? The time to escape potential well is a constant. So what is this constant? It's the minimum of v minus the minimum of v on the boundary. What is this? In chemistry, this is known as the energy barrier. This is the energy barrier between the minimum of V. So this is the energy barrier. Right? And this is called, what is this law that we have derived?
Arrhenius.
That's right, this is the Arrhenius law of chemical reaction, except now. Usually this is given in student in chemistry with a constant. Now we have calculated all constants. We have not calculated how they, first of all, there is a term here that depends. KT in chemistry is what? Epsilon, I'm sorry, is what? The energy, kT. K Boltzmann temperature, this is epsilon. So we know that there is a kT here. This is the energy, this is the time it takes, this is the exponential time. And the constant K depends exactly on the second derivative of the potential of one of the determinant that you have to count about the point. That's the story. Right? So we have, this is why all of this is important. It comes to the classical Arrhenius chemical reaction, except that now you see the dependency, how it depends on the second derivative of the potential restricted on the boundary. So you cannot do everything in dimension 1, you just do dimension 1, so you get the just the first, the second derivative of your function. This is n dimension. So the output of all of this, that we know that the mean first passage time to escape from a potential well like this is going to be exponential in 1 over the noise. This is only true if you start inside. If we start at the layer, we have seen that this is not exponential. This is the V epsilon behaves, goes to 0, the mean first passage time behaves with this function. And of course, this is important if you look at channels. Now we know exactly if you start in the boundary layer, if you have an ion, how long it takes for the ion or particle to escape the channel when you are not inside the potential, when you are just at the boundary, which is very important to do the calculation. Okay.
I mean, is there any result known for shallow potential wells?
Shallow potential, you cannot
Where
do.
basically that approximation doesn't apply?
That's right. Now you have to be more specific about what you want to look at. For shallow potential, this is true. I mean, for shallow potential, basically, what is important, if you do a numerics or whatever, is this formula. Because this formula doesn't assume you express this in terms of the potential. The mean time in this domain is expressed of this. Now, for example, if epsilon is not small, for example, if epsilon, I don't know exactly what you have, but if V, for example, or V divided by epsilon is shallow and it is small actually, it's the opposite of what we have done, then you can do an expansion, a Taylor expansion of the exponential in terms of the variable x here.
It's just about like epsilon.
Yeah, if it's just about epsilon, then you understand, yet you have to calculate everything. There is no shortcut.
Right.
And look, this is so this is basically the knowledge of people until the end of the 70s. You are now, we are just 30 years
40.
Yeah, before our time, before today's time. But it shows you the methods. That was the most important, the methods. You see, and this is what is written in all chemistry, theoretical chemistry books. Except that now we have developed the entire artillery that can be applied to any equations in terms of the applied mass. All right. So I'll conclude with a remark, and I think for today it's enough because we have worked a lot. It's time to enjoy the sun. I'm going slower than expected, but I understand it's important that we go slowly in all of this. Okay, so the comments that I'm going to give you is that there are two comments, and then we are free to go. There are two comments. One is that lambda, really the reaction rate is 1 over the mean first passage time, tau epsilon, which we write this way. So this is called the backward chemical reaction. Right? This is the rate at which two molecules dissociate when one is trapped by the potential of one. So when you have a reaction A that gives AB, now you understand that this A plus B, or B plus A that gives AB, the dissociation rate, K minus 1, is exactly what we have calculated. Two things going apart. And now what you, to answer your question, in general, if you're interested in the event that two particles have not dissociated, which is the survival probability, and if you look at the dynamics, so this is mean first passage time. Now if we look at the time-dependent question, time-dependent problem, and we are interested in, it's called S of t, which is a survival probability. That is, at time t, what's the probability that you didn't get any dissociation? So no dissociation at time less than t. So, which means that this is equal to the probability that you have not escaped from the domain. That is, t is larger than t. And this can be expressed in terms of the integral of the Fokker-Planck equation, pt of x, condition that you started at any point x, any point y, this is dx. And in general, if it's not since we can always expand in eigenvalue and eigenfunction the operator, and they are exponentially distributed, in general what we get here is the sum of the integral of a constant exponential, so constant that depends on x. So whatever, I will write it this way, like constant ck. This is exponential minus lambda k t over k, where lambda k are the eigenvalues of the Fokker-Planck equation, which was Fokker-Planck equation that we have discussed last time. So if you have a single exponential, single one, then the process is actually Poissonian. If a single one means, for example, the time is not 0 and you know that you're waiting at the long event, so you're going to have something of the form exponential lambda 1 t. And lambda 1 here, this is exactly the lambda 1 that we calculated, 1 over the mean first passage time tau that we calculated. So your particles are going to come at a Poissonian rate of dissociation, and the rate of dissociation is the mean first passage time. If, of course, we have multiple exponential rates, they cannot be dissociate one to the other, then in principle it's a sum of exponential, which is much more tricky to study. All right, but if the well is sufficiently deep, we can approximate this infinite sum by just the first one, because this is what defines really the tail of the distribution. You are interested in rare event because it's a rare event to exit, and then they are distributed with the Poisson law. All right, so this is why people in chemistry, they can describe chemical reaction using Gillespie algorithm or Poissonian, because it's Poissonian. You approximate the rate as Poissonian with a single exponential. Sometimes it's not like this, and then it's a mess. You have to reconstruct your understanding about the system. All right, we did a lot today. It's impossible to look at this kind of calculation, you know, without going slowly again all these steps. We should go slowly about all the steps. You can go in the classical books to know that you should be able with the class to really start to read the modern approach of a chemical reaction. And then we'll continue on this. Next week I'm not here. Next week I'm in the USA. And then we'll resume in 2 weeks. In 2 weeks from now, I will start doing narrow escape slowly. How to escape through a small hole, and we can combine how to escape through a small hole when you have a potential. We can combine things in a very different manner. Okay, so again, it takes time to understand all what we have done today. There's a lot. There is maybe 100 years of applied math summarized in terms of boundary layer, Laplace methods, asymptotics, inner solution, outer solutions. But this is the basic. This is really any theoretical chemist, applied mathematicians, statistical physics. This is really the routine stuff. Something you should know. That's it. So we'll continue in 2 weeks.
So in chemistry, when the energy value is very deep, means the reaction is very real.
When the potential is very deep,
Yeah, in chemistry. So
in chemistry means you have a Poissonian rate, Poissonian process.
then the reaction is very rare to happen. Or?
Very what? Very rare. It's a rare event, sure. Rare events are what is driving the interesting thing in our life and the life of chemistry. Those are rare events. That's why it's very hard to detect them. It's very hard because of the rare events and they are exponentially distributed.
Yeah.
But I'm surprised, not in chemistry, in here they don't give this kind of lecture about this.
I don't know, I haven't started here, so.
Okay. This is really the basic. This is really